Tonight, we're going to explore something that sounds like the ultimate space exploration challenge, but is actually physically impossible with any technology we can imagine: Jupiter missions. You've probably seen the concept art, the sci-fi depictions of floating cities in Jupiter's clouds, the dreams of harvesting helium-3 from the atmosphere, or establishing research stations in orbit. But here's what they left out. There is no going to Jupiter in any meaningful sense. Not because we lack the ambition or the funding, but because Jupiter isn't a place you can go. It's an impossible destination for humans, where the radiation alone would be fatal within hours, where the gravity would make leaving physically impossible, and where there's no solid surface to land on, even if you survive the journey. By the end of tonight, you're going to understand exactly why Jupiter represents an absolute boundary for human exploration, why even our most advanced robotic probes barely survive flyby missions, and why anyone who went to Jupiter wouldn't just fail to return. They'd face conditions so extreme that survival itself becomes the only mission. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what Jupiter actually is, because this is where most people's understanding breaks down. Jupiter isn't like Mars or Earth, or any rocky planet you're familiar with. Jupiter is a gas giant, which is a misleading name, because it suggests there's just a lot of gas floating around, with maybe a solid core underneath. The reality is far stranger and far more hostile. Jupiter is essentially a failed star, a ball of hydrogen and helium so massive it generates intense heat and pressure in its interior. If Jupiter had been about 80 times more massive, it would have ignited nuclear fusion and become a second sun in our solar system. As it is, Jupiter contains more mass than all the other planets combined, about 318 times Earth's mass, packed into a sphere roughly 11 times Earth's diameter. That mass creates gravity 2.5 times stronger than Earth's at the cloud tops, and it only gets more intense as you go deeper. But here's the critical detail that makes Jupiter fundamentally different from any place humans could visit. There is no surface. This isn't like landing on a planet with thin atmosphere where you descend through clouds and eventually touch down on solid ground. Jupiter's atmosphere just keeps getting denser and hotter and more pressurized as you go deeper. The hydrogen gas gradually transitions to liquid hydrogen, then to metallic hydrogen under pressures millions of times Earth's atmospheric pressure. There's no clear boundary, no moment where you'd hit something solid. You just descend into increasing density and pressure until your spacecraft was crushed into atomic particles. The temperature at Jupiter's core is estimated at 43,000 degrees Fahrenheit, hotter than the surface of the Sun. The pressure is estimated at 45 million times Earth's sea level, atmospheric pressure. No material we know of could withstand these conditions. Diamond would be crushed into powder. Titanium would vaporize. Any theoretical spacecraft would be destroyed long before reaching whatever core might exist at the center. So when we talk about going to Jupiter, we're not talking about landing on the planet. We're talking about entering orbit around it, or possibly attempting to land on one of its moons. And both of these options present challenges that make Mars colonization look trivial by comparison. The first challenge is simply getting there. Jupiter orbits at an average distance of 484 million miles from Earth. When Earth and Jupiter are on the same side of the Sun, at closest approach, they're separated by about 390 million miles. When they're on opposite sides of the Sun, the distance extends to about 600 million miles. For comparison, Mars at its farthest is 250 million miles away. Jupiter is typically twice as far as Mars, and that distance compounds every problem of interplanetary travel. The journey time to Jupiter, with current chemical propulsion technology, is 18 months to 2 years. That's using gravitational assists from other planets to build up speed and following the most efficient transfer orbit. The Galileo spacecraft, launched in 1989, took 6 years to reach Jupiter because it took a circuitous route using gravitational assists from Venus and Earth. The Juno spacecraft, launched in 2011, took 5 years despite following a more direct path. New Horizons, the fastest spacecraft ever launched, flew past Jupiter in just 13 months, but it was moving so fast it couldn't stop. It used Jupiter for a gravitational slingshot toward Pluto. For a crewed mission, you'd want to minimize travel time to reduce radiation exposure and life support requirements. 18 months to 2 years is about the minimum possible with chemical rockets. That's 18 months to 2 years living in a cramped spacecraft, farther from the Sun where solar panels become less effective, exposed to cosmic radiation with no protection from Earth's magnetic field. And unlike Mars, where you can wait for a return window, Jupiter's orbital period is nearly 12 Earth years. The orbital mechanics for return trajectories are far more complex. You might need to wait several years for the right alignment, or use complex multi-planet gravity assists to get back. A round-trip mission to Jupiter could easily take 7 to 10 years total. That's 7 to 10 years away from Earth, with all the physical degradation we discussed for Mars missions, multiplied by the longer duration. Bone loss, muscle atrophy, radiation exposure, psychological stress, all accumulating over nearly a decade. No human has ever spent more than 14 consecutive months in space. The longest single space mission was 437 days by Russian cosmonaut Valery Polyakov on the Mir space station. He needed months of rehabilitation after returning to Earth. A Jupiter mission would be 3 to 5 times longer in deep space, without the possibility of emergency evacuation or resupply from Earth. Then there's the radiation, and this is where Jupiter becomes truly lethal. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind, creating radiation belts similar to Earth's Van Allen belts, but vastly more intense. The radiation environment around Jupiter is the most extreme in the solar system. Europa, one of Jupiter's moons that orbits within the radiation belts, receives about 5,400 rem of radiation per day at its surface. That's more than 5,000 times the dose that would kill a human. An unshielded human standing on Europa's surface would receive a lethal dose of radiation in less than 1 day. For comparison, the total radiation exposure on a 3-year Mars mission is about 100 to 140 rem. On Europa, you'd receive that much radiation in about 20 minutes. And Europa isn't even the worst. Io, the innermost large moon, orbits even deeper in Jupiter's radiation belts and receives exponentially higher radiation doses. Even in Jupiter orbit, staying outside the most intense radiation belts, you'd be exposed to radiation levels thousands of times higher than in interplanetary space. The spacecraft itself would need massive shielding, which adds weight, which requires more fuel, which makes the mission more expensive and difficult. Electronics would fail rapidly under this radiation bombardment. Computer chips would suffer bit flips and permanent damage. solar panels would degrade quickly. Biological tissue would be shredded at the molecular level. DNA would break down, cells would die, and no amount of shielding practical for a spacecraft could reduce the radiation to safe levels. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, was designed with radiation-hardened electronics. It still suffered multiple system failures due to radiation damage over its mission lifetime. The Juno spacecraft, currently orbiting Jupiter, uses a titanium vault to protect its most sensitive electronics. Even with this protection, its electronics are being slowly destroyed by radiation. Juno's mission is designed to end before radiation damage becomes fatal to the spacecraft. For humans, there's no vault thick enough. You'd need meters of shielding, which would make the spacecraft impossibly heavy. And even if you could shield the crew compartment adequately, you'd still need to go outside for repairs, maintenance, and any kind of exploration. Every EVA would be a death sentence. Let's talk about what it would actually mean to try to establish a presence at Jupiter. Since you can't land on the gas giant itself, the only option is the moons. Jupiter has 95 confirmed moons, and probably more that haven't been discovered yet. The four largest, discovered by Galileo in 1610, are Io, Europa, Ganymede, and Callisto. These are substantial worlds in their own right. Ganymede is larger than the planet Mercury. Europa and Callisto are both larger than Earth's moon. These moons might seem like possible destinations, places where you could land, establish a base, and conduct research. But each one presents unique and nearly insurmountable challenges. Io is the most volcanically active body in the solar system. It has hundreds of active volcanoes constantly erupting, reshaping the surface. The volcanic activity is driven by tidal heating. Jupiter's massive gravity, combined with gravitational tugs from Europa and Ganymede, squeezes and flexes Io like a stress ball. This constant flexing generates enormous heat through friction, melting rock, and driving volcanic eruptions that can throw plumes of sulfur and sulfur dioxide hundreds of miles into space. The surface of Io is constantly being covered by new volcanic deposits. Lava lakes dot the landscape. The atmosphere, thin as it is, consists of sulfur dioxide gas vented from volcanoes. Standing on Io, you'd see Jupiter filling half the sky, an enormous banded sphere of swirling clouds. You'd see other moons crossing in front of Jupiter or casting shadows on its cloud tops. And you'd be standing on ground that's literally melting beneath you, while volcanic plumes erupt around you and radiation bombards you from above. Io orbits deep within Jupiter's radiation belts. The radiation there is so intense that no human could survive more than minutes, even with the best shielding. Electronics would fail almost immediately. Any base on Io would need to be buried deep underground to have any chance of protecting inhabitants from radiation, and even then, the volcanic activity would make long-term survival nearly impossible. Io is hell, in the most literal sense. It's not a place humans could ever live. Europa is more intriguing, because underneath its icy surface lies a global ocean of liquid water that might contain twice as much water as all of Earth's oceans combined. This ocean is kept liquid by tidal heating from Jupiter, the same process that drives Io's volcanism, but less extreme at Europa's greater distance. The ice shell covering the ocean is probably 10 to 15 miles thick. The surface shows cracks, ridges, and chaos terrain, where the ice has broken up and refrozen, evidence of the ocean below, moving and shifting. Europa is one of the best candidates in the solar system for finding extraterrestrial life. Wherever we find liquid water on Earth, we find life. And Europa has an enormous amount of liquid water that's been stable for billions of years. There might be hydrothermal vents on the ocean floor providing energy for microbial ecosystems similar to those around Earth's deep-sea vents. This makes Europa incredibly interesting, scientifically, and missions are being planned to orbit Europa and possibly land on its surface. But for humans, Europa presents the same radiation problem as Io, just slightly less severe. Europa still orbits well within Jupiter's radiation belts. Radiation on Europa's surface is about 5,400 rem per day. A human would receive a lethal dose in hours. Any surface operations would be impossible without radiation shielding so thick and heavy, it's impractical. You'd need to drill through miles of ice to reach the ocean, and then somehow operate in a dark, high-pressure environment beneath an alien ice shell on a moon bombarded by lethal radiation. The engineering challenges are staggering, far beyond anything we've attempted. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. This magnetic field provides some protection from Jupiter's radiation, creating a mini-magnetosphere. Radiation levels on Ganymede's surface are lower than on Europa or Io, though still far higher than anywhere on Earth. Ganymede has a mix of older, heavily cratered terrain and younger, grooved terrain that suggests geological activity in the past. It likely has a subsurface ocean like Europa, buried beneath multiple layers of ice and rock. Ganymede orbits far enough from Jupiter that radiation, while still dangerous, might be manageable with sufficient shielding. If you had to choose a Jovian moon for a base, Ganymede would be the least terrible option. But Ganymede is still 484 million miles from Earth, at best. It's still orbiting a planet with deadly radiation belts. It's still a frozen world with no atmosphere, where surface temperatures average minus 260 degrees Fahrenheit. Any base would need to be completely self-sufficient for years because resupply missions would take 2 years each way. If anything critical broke, if life support failed, if food production stopped, everyone would die long before help could arrive from Earth. Callisto orbits farthest from Jupiter among the Galilean moons. It's outside the most intense radiation belts, making it the safest of the large moons in terms of radiation exposure. Callisto is heavily cratered, with one of the oldest surfaces in the solar system, suggesting minimal geological activity. It might have a subsurface ocean, but this is less certain than for Europa or Ganymede. Callisto's main advantage is lower radiation. Its main disadvantage is that it's even farther from everything. Communication delays between Callisto and Earth would be 35 to 52 minutes each way. Any conversation with mission control would take over an hour for a single exchange. You'd be truly on your own, making decisions without Earth's guidance, living or dying based on your own resourcefulness. Now, let's confront the fundamental impossibility of return from Jupiter's moons. Even if you somehow survived the journey, established a base on one of the moons, and managed to stay alive despite the radiation and isolation, getting back to Earth presents challenges that might be physically impossible. Jupiter's gravity, well, is immense. Escape velocity from Jupiter's cloud tops is 134,000 miles per hour. That's 5 times higher than Earth's escape velocity. From the surface of Ganymede, which has its own gravity, you'd need to escape Ganymede first, then escape Jupiter's gravitational influence. The fuel requirements for this are astronomical. We're not talking about the difficult but manageable fuel requirements for a Mars return mission. We're talking about fuel masses so large they make chemical rocket propulsion essentially useless. To put this in perspective, the New Horizons spacecraft, the fastest object ever launched from Earth, achieved a speed of about 36,000 miles per hour relative to Earth. That was fast enough to reach Pluto in under 10 years. But it's nowhere near the 134,000 miles per hour needed to escape Jupiter. New Horizons didn't slow down at Jupiter. It used Jupiter's gravity to speed up even more for its journey to Pluto. Actually escaping from Jupiter's system, starting from rest on one of the moons, would require velocity changes far beyond what chemical rockets can efficiently provide. You'd need nuclear propulsion or some future technology we haven't developed yet. And you'd need to carry all that propulsion capability with you from Earth, because there's no way to manufacture fuel on Jupiter's moons. Europa's ice could theoretically provide water for electrolysis to produce hydrogen and oxygen, but the energy requirements would be enormous, and you'd still have the radiation problem during any surface operations to extract the ice. The other option is ion drives, or electric propulsion, which can achieve much higher speeds over time using less propellant, but electric propulsion produces very low thrust. It works for unmanned spacecraft that can spend months or years gradually accelerating. For humans who need to minimize time in Jupiter's radiation environment, slow acceleration isn't acceptable. You'd need to escape quickly, and that requires high-thrust chemical or nuclear rockets, which brings us back to the impossible fuel requirements. There's also the problem of timing and orbital mechanics. Launch windows from Earth to Jupiter align roughly every 13 months, but launch windows from Jupiter back to Earth depend on where both planets are in their orbits. Jupiter's orbital period is almost 12 Earth years. The geometry gets complicated quickly. You might arrive at Jupiter and find you need to wait several years for a favorable return window. During those years, radiation exposure continues, life support systems age and fail, and the psychological toll mounts. And all of this assumes you have fuel for the return journey, which you probably don't, because the mass of that fuel would have made the initial mission impossible. Let me paint a picture of what a Jupiter mission would actually look like if anyone were insane enough to attempt it. You'd launch from Earth using the most powerful rockets available, probably multiple launches assembling a spacecraft in Earth orbit. The spacecraft would need heavy radiation shielding, years of life support consumables, power generation adequate for deep space where solar panels are less effective, and either a nuclear reactor or radioisotope thermoelectric generators. You'd spend 18 months to 2 years traveling outbound, watching the sun shrink to a bright star in the distance. As you approach Jupiter, the planet would grow from a bright point of light to a massive sphere filling your viewport. The cloud bands would become visible, swirling in complex patterns. The Great Red Spot, a storm larger than Earth that's been raging for over 400 years, would be a huge oval of churning atmosphere. You'd see the moons, tiny disks resolving into worlds, crossing in front of Jupiter's face or disappearing into its shadow. And you'd see the radiation levels climbing on your instruments, climbing to dangerous levels, climbing to lethal levels. Your spacecraft would enter orbit around Jupiter or one of its moons, and immediately you'd face the radiation onslaught. Even the best shielding would only reduce the radiation, not eliminate it. You'd be accumulating doses far beyond any safety limits, knowing that every day increases your cancer risk, damages your DNA, weakens your immune system. If you attempted to land on one of the moons, you'd need to account for the moon's gravity, the lack of atmosphere for aerobraking, and the rough terrain. Ganymede's gravity is about 1/7 of Earth's, enough that landing requires significant fuel for deceleration. Once on the surface, you deploy habitats, preferably buried under regolith for radiation protection. You'd start trying to operate scientific instruments, explore, maybe drill into the ice if you're on Europa or Ganymede. Every moment outside the habitat is dangerous. Radiation exposure accumulates with every EVA. Equipment fails faster than expected due to radiation damage. Solar panels degrade. Batteries lose capacity. Computer systems experience errors and failures. Meanwhile, you're alone. Communication with Earth has a delay of 35 to 52 minutes each way. If something goes wrong, you can't get advice in real time. You either solve the problem yourself or you die. Resupply is impossible on timescales that matter. If you run out of critical supplies, if life support fails, if someone gets seriously injured or ill, there's no rescue. You're 484 million miles from Earth with no way home. And here's the truly dark part. Even if everything went perfectly, even if you survived the radiation, maintained your equipment, avoided accidents, and stayed psychologically stable, when the time came to leave, you probably couldn't. The fuel requirements to escape Jupiter's gravity well are so extreme that bringing enough fuel from Earth is impractical. Manufacturing fuel on site is impossible because there's no accessible resources, and the radiation makes surface operations nearly impossible. You'd be trapped, not by choice, not by mission failure, but by physics. Jupiter's gravity is an inescapable well that you fell into with no realistic way to climb back out. You'd live out the rest of your life on a frozen moon, watching Jupiter hang in the sky, knowing Earth exists somewhere in the darkness, 484 million miles away, forever out of reach. Eventually, radiation exposure would cause cancer, or equipment would fail catastrophically, or supplies would run out, or psychological breakdown would make continued survival impossible. The mission wouldn't end with a triumphant return to Earth. It would end with death on an alien moon orbiting a planet humans were never meant to visit. The comparison to historical exploration breaks down completely when we talk about Jupiter. When Polynesians sailed across the Pacific or Europeans crossed the Atlantic, they faced danger and uncertainty, but they were traveling to places fundamentally compatible with human life. The islands and continents they reached had breathable air, drinkable water, food sources, and environments where humans could survive without technology. Jupiter's moons are the opposite. They're fundamentally incompatible with human life in every possible way. No air, no water except frozen solid, no food, temperatures hundreds of degrees below zero, radiation that would kill you in hours or days. You can only survive there, inside artificial environments, completely dependent on technology that has no redundancy and no possibility of replacement if it fails. This is more like trying to live on the surface of the sun than like any historical human exploration. It's not just difficult. It's a category of challenge we've never faced and might never be able to overcome. Some people might argue that we should send missions to Jupiter's moons despite these challenges because of the scientific value. Europa's ocean might harbor life, and that discovery would be one of the most important in human history. But we can study Europa with robotic missions. The Europa Clipper mission, scheduled to launch in 2024, will orbit Jupiter and make multiple close flybys of Europa, studying its ice shell, measuring its ocean depth, and searching for plumes of water vapor that might contain organic molecules from the ocean below. Robotic missions can tolerate radiation levels that would kill humans. They don't need life support or food or psychological support. They can be designed to operate for months or years and then fail. Mission accomplished. We don't need humans at Jupiter to do science. In fact, humans would be a liability. Massive life support requirements, high cost, constant radiation exposure, psychological fragility, all for minimal advantage over robots. The argument for human exploration of Mars is that humans can explore more efficiently than robots, make decisions in real time, adapt to unexpected situations. At Jupiter, those advantages are overwhelmed by the sheer difficulty of keeping humans alive. You'd spend so much effort on survival that actual exploration would be minimal. There's also the question of whether we should go to Jupiter even if we could. Europa's ocean might contain life, and if it does, sending humans there risks contaminating that ecosystem with Earth microbes. Despite sterilization procedures, it's nearly impossible to completely sterilize a spacecraft or a human. We carry trillions of microbes in and on our bodies. If even a few of those microbes reached Europa's ocean, they might multiply and spread, potentially outcompeting or destroying native European life. This is called forward contamination, and it's a serious concern for any mission to potentially habitable environments. The scientific community has protocols for planetary protection, requirements for sterilization and contamination control. Robotic missions can be sterilized to very high standards. Human missions cannot. If we sent humans to Europa, we'd almost certainly contaminate it. That contamination might destroy the very thing we went there to study. It would be an irreversible tragedy, the destruction of an alien biosphere through carelessness. Let me address the technological optimism argument. Some people say that technology will improve, that future propulsion systems will make Jupiter missions feasible, that advanced radiation shielding will protect crews, that we'll develop closed-loop life support that can operate for decades. Maybe some of that is true. Nuclear thermal or nuclear electric propulsion could reduce travel times and fuel requirements. Advanced materials might provide better radiation shielding. Artificial gravity through rotating spacecraft might prevent some of the physical degradation from long-term weightlessness. But these are incremental improvements, not game changers. They don't solve the fundamental problems. Jupiter is still 484 million miles away. Its radiation belts are still lethal. Its gravity well is still nearly inescapable. There's still no solid surface to land on. You can't engineer your way out of physics. The distances are set by orbital mechanics. The radiation is produced by Jupiter's magnetic field, which we can't change. The gravity is a consequence of Jupiter's mass, which is fixed. No amount of technological advancement changes these fundamental facts. What about the argument that we should establish a presence at Jupiter for resource extraction? Jupiter's atmosphere contains helium-3, a rare isotope that could theoretically be used for fusion reactors. If we ever develop practical fusion power, helium-3 might be valuable. But extracting it from Jupiter's atmosphere would require descending into the pressure and heat and radiation of the upper atmosphere, scooping up gas and escaping back to orbit. The energy cost of this process almost certainly exceeds the energy value of the helium-3 you'd extract. You'd spend more fuel escaping Jupiter than you'd gain from the helium-3, even if fusion worked perfectly. It's economically nonsensical. The asteroids are much better sources for any resources we might want. They're easier to reach, have no gravity well to escape, no radiation to deal with, and contain metals and water ice in easily accessible forms. There's no economic reason to go to Jupiter. So, where does this leave us? Jupiter is a planet we can study from a distance with telescopes and flybys. We can send robotic orbiters like Juno and Galileo to study the planet's atmosphere, magnetic field, and interior structure. We can send dedicated missions like Europa Clipper to study the moons. But humans will never walk on Jupiter's moons. We'll never establish bases there. We'll never mine resources from Jupiter's atmosphere. The challenges are too extreme, the dangers too severe, the costs too high, and the benefits too small. Jupiter represents a boundary, a limit to human exploration. We can go to the moon. We might establish bases on Mars, though as we discussed in another video, those would be one-way trips. We might visit asteroids or build habitats in free space. But Jupiter is beyond our reach, not just technologically, but fundamentally. It's too far, too dangerous, too alien for human presence. This isn't defeatism or lack of imagination. It's acceptance of physical reality. The universe has laws, and those laws constrain what's possible. We can't travel faster than light, no matter how advanced our technology becomes. We can't survive in Jupiter's radiation belts, no matter how good our shielding is. We can't escape Jupiter's gravity well without absurd amounts of fuel, no matter what propulsion system we use. These aren't engineering challenges to be solved with enough effort. They're fundamental limits imposed by physics. Recognizing these limits doesn't diminish the wonder of Jupiter. It's still an incredible world, a massive sphere of swirling gas and liquid and metallic hydrogen, with a magnetic field that creates auroras. Thousands of times more powerful than Earth's. It has a system of moons that are worlds unto themselves, each unique, each fascinating. The Great Red Spot is a storm that's been raging since before telescopes were invented. Jupiter shaped the early solar system, its gravity shepherding asteroids and comets, protecting the inner planets from some impacts and causing others. Jupiter is magnificent and important and worthy of study. We just need to study it from a distance. The future of Jupiter exploration is robotic. Orbiters that can tolerate radiation and send back data for years. Atmospheric probes that descend into the clouds, measuring temperature and pressure and composition before being crushed. Landers on the moons, drilling through ice, studying surface chemistry, searching for signs of life. These missions will teach us about planetary formation, atmospheric dynamics, magnetic field generation, and possibly the origin of life. They'll expand our understanding of our solar system and of planetary systems around other stars. But they won't involve humans standing on Ganymede, looking up at Jupiter. They won't involve colonies on Europa mining ice. They won't involve cities floating in Jupiter's clouds. Those are fantasies, fun to imagine but physically impossible. This has been a darker journey than most space exploration discussions. Usually, when we talk about planets and moons, there's optimism about future missions, about human expansion into the solar system, about establishing our presence on other worlds. Jupiter doesn't allow that optimism. Jupiter forces us to confront limits, to acknowledge that some places are simply beyond human reach. And maybe that's valuable in its own way. Maybe recognizing our limits helps us focus our efforts where they matter. We should absolutely work toward Mars colonization, despite its challenges. Because Mars is reachable. We should establish permanent bases on the Moon because it's practical. We should explore asteroids because they're accessible and resource-rich. But we should accept that Jupiter is a place we'll never go, that its moons will remain untouched by human hands, that the Jovian system will forever be the realm of robots and remote sensors. Thank you for joining me on this sobering exploration of why anyone who goes to Jupiter will never come back. Not because they'd choose to stay, not because political or economic factors would prevent return, but because they'd be gone, long before return was possible. The radiation would kill them, the distance would isolate them, the gravity would trap them, and the sheer hostility of the environment would ensure that any human mission to Jupiter would be a one-way trip to death. Jupiter is beautiful from a distance. It's scientifically fascinating. It's worthy of study and wonder. But it's not a place for humans. It never will be. And accepting that reality is part of understanding our place in the solar system. Some worlds are for exploring. Some are for settling. And some are for admiring from afar, marveling at their complexity and power, while acknowledging that they're fundamentally alien to us. Jupiter is the third category. It's a giant that we can study but never touch, a planet that will forever remain beyond the reach of human exploration. But let me be more specific about why the physics makes this impossible, because understanding the details helps clarify just how insurmountable these challenges are. Let's start with the journey itself, and what happens to spacecraft and humans during the years it takes to reach Jupiter. Current chemical rocket technology can get us to Jupiter in about 18 months to 2 years if we follow an efficient Hohmann transfer orbit. This is the minimum energy path between two planets, an elliptical orbit that touches Earth's orbit at one end and Jupiter's orbit at the other. You launch when Earth and Jupiter are positioned correctly, coast through space for months, and arrive when Jupiter is at the right point in its orbit. The spacecraft needs to carry enough velocity to leave Earth's gravitational influence, which means launching at about 25,000 miles per hour relative to Earth. Once you're in interplanetary space, you're coasting. There's no air resistance, no friction, just the pull of the sun's gravity curving your path into an ellipse. As you move outward from the sun, you slow down slightly because you're climbing out of the sun's gravity well. By the time you reach Jupiter's orbit, you're moving at a different speed than Jupiter itself is moving. Jupiter orbits the sun at about 29,000 miles per hour. When you arrive, you're moving about 37,000 miles per hour relative to the sun. But Jupiter is moving slower because it's farther from the sun. The relative velocity between your spacecraft and Jupiter is significant, maybe 8,000 to 10,000 miles per hour, depending on exact trajectory. This means you can't just enter orbit around Jupiter. You'd fly right past unless you slow down. Slowing down requires firing rockets, which requires carrying fuel. Entering Jupiter orbit requires a delta V change, a velocity change, of roughly 6,000 to 8,000 miles per hour. This is enormous compared to entering Mars orbit, which requires about 3,500 miles per hour delta V. The fuel requirement grows exponentially with delta V because of the rocket equation. You need fuel to slow down, but that fuel has mass, so you need more fuel to carry the fuel, and that fuel has mass, and so on. For a large spacecraft with crew and life support and supplies, entering Jupiter orbit might require fuel mass equal to or greater than the mass of the rest of the spacecraft. You'd be launching a spacecraft that's 50% fuel by mass just to enter Jupiter orbit. And that's before you account for landing on a moon, taking off again, escaping Jupiter's gravity, and returning to Earth. The life support requirements for 18 months to 2 years outbound are staggering. An average human needs about 2.2 pounds of food per day, about 1 gallon of water per day if water is recycled efficiently, and about 2 pounds of oxygen per day. For a crew of 4 traveling for 2 years, that's about 6,400 pounds of food, 7,300 pounds of water if you have perfect recycling, and 5,800 pounds of oxygen if recycled perfectly. But recycling is never perfect. Water recycling on the ISS achieves about 93% efficiency. 7% is lost and must be replaced. Over 2 years, those losses add up to significant mass. You might need to launch with 10,000 to 15,000 pounds of water to account for losses. Oxygen recycling also has losses. You need to bring extra, and food can't be recycled. It's consumed and converted to waste. You need enough food for the entire journey. Add in the mass of the crew, their personal items, tools, scientific equipment, computers, communications gear, and the spacecraft structure itself. And you're looking at total mass of 30,000 to 50,000 pounds just for basic survival on a 2-year outbound journey. Now add fuel for entering Jupiter orbit, fuel for any landing attempts, fuel for escaping Jupiter, fuel for returning to Earth. The numbers become absurd. You might need to launch 200,000 to 300,000 pounds or more from Earth. Current heavy-lift rockets can put about 150,000 pounds into low Earth orbit. You'd need multiple launches, assembly in Earth orbit, and perfect execution of an incredibly complex mission just to get to Jupiter. And that's assuming nothing goes wrong. What goes wrong on a 2-year journey through deep space? Equipment fails. Solar panels degrade from micrometeorite impacts and radiation exposure. Computer systems experience bit flips from cosmic rays. Pumps and fans wear out. Seals leak. Filters clog. On the ISS, which orbits within Earth's protective magnetic field and receives regular resupply missions, equipment failures occur frequently. Pumps need replacement. Computer modules fail and are swapped out. Filters are changed. Parts wear out and break. Astronauts spend significant time on maintenance and repairs, and when something breaks that they can't fix, a replacement is sent on the next resupply flight. On a Jupiter mission, there are no resupply flights. Everything you might need must be carried from Earth. Redundancy is critical. Every vital system needs backups, and backups for the backups. But redundancy adds mass, which requires more fuel, which adds more mass, and the exponential growth of required launch mass makes missions impossible beyond a certain complexity. You reach a point where adding more redundancy requires so much additional fuel that you can't launch the mission at all. It's a vicious cycle with no good solution. The psychological challenges of 2 years in deep space are also severe and poorly understood. The longest anyone has spent in continuous spaceflight is 14 months. Most ISS missions are 6 months. We have limited data on psychological effects of longer missions, but studies on Antarctic research stations, submarine crews, and isolated groups suggest that 18 months to 2 years is near the breaking point for small groups. Conflicts develop. People become irritable, withdrawn, or depressed. Minor annoyances magnify into major grievances. The novelty of the environment wears off and is replaced by grinding monotony. Every day is the same. Same people, same small spaces, same recycled air and water, same packaged food. On the ISS, crews can look out windows and see Earth. They can communicate with family and friends with minimal delay. They know they're going home in 6 months. On a Jupiter mission, Earth becomes a tiny blue dot lost in the sun's glare. Communication delays grow from seconds to minutes as you move outward. By the time you're halfway to Jupiter, round-trip communication takes 20 to 30 minutes. You send a message and wait 15 minutes for it to reach Earth. Then wait another 15 minutes for the response. Real-time conversation is impossible. You're alone, in a way no ISS astronaut has ever been. And you know, the mission is years from completion. There's no going home in 6 months. You're committed to the full duration, whether you want to be or not. As you approach Jupiter, the view changes from a bright star to a tiny disk to a massive planet filling your forward viewport. The cloud bands become visible, parallel stripes of white, brown, tan, and orange stretching across the planet. These bands are zones of upwelling and downwelling gas, driven by Jupiter's rapid rotation and internal heat. Jupiter rotates once every 10 hours, the fastest rotation of any planet in the solar system. This rapid spin creates intense winds that blow in opposite directions in adjacent bands, sometimes at speeds of 300 to 400 miles per hour. The Great Red Spot becomes visible, an enormous oval storm that's larger than Earth. You realize that the planet you're approaching is not just big, it's incomprehensibly large. 11 Earths could fit side by side across Jupiter's equator. More than 1,300 Earths could fit inside Jupiter's volume. The scale is difficult to process, even when you're seeing it directly. And as you get closer, the radiation measurements start climbing. Jupiter's magnetic field extends millions of miles into space, far beyond the planet itself. This magnetosphere traps charged particles from the solar wind, creating vast donut-shaped regions of intense radiation surrounding the planet. The inner radiation belts, close to Jupiter and extending out to about twice Jupiter's radius, are the most intense. Particles in these belts have energies of millions of electron volts. They would penetrate spacecraft walls, damage electronics, and tear through human tissue. Your spacecraft has radiation shielding, probably layers of polyethylene or water tanks surrounding the crew compartment. But even the best practical shielding can only reduce radiation exposure, not eliminate it. As you enter Jupiter's magnetosphere, radiation levels inside the spacecraft start climbing. 10 times background, 100 times, 1,000 times. Your instruments measure the dose rate in rem per hour, and it keeps increasing. The crew would be confined to the most heavily shielded area of the spacecraft, minimizing movement, minimizing exposure. But there's no complete protection. Every hour in Jupiter's radiation belts adds to your cumulative dose. Every rem increases cancer risk, damages DNA, suppresses immune function. The decision point approaches. Do you enter orbit around Jupiter itself, staying outside the worst radiation belts, but still experiencing dangerous exposure? Or do you aim for one of the outer moons like Ganymede or Callisto, where radiation is somewhat less severe? Either choice involves enormous fuel expenditure to change your velocity. Remember, you're approaching at 8,000 to 10,000 miles per hour relative to Jupiter. To enter orbit, you must fire retro rockets, burning fuel to slow down. The longer and harder you burn, the more fuel you consume. Entering a capture orbit around Jupiter requires velocity change of 6,000 to 8,000 miles per hour. That's an enormous burn, possibly 20 to 30 minutes of continuous rocket firing. During this burn, you're committed. If the engines fail, You fly past Jupiter and continue into deep space with no way to return. If they burn too long, you might descend into the atmosphere and be destroyed. If they burn too little, your orbit might be highly elliptical, carrying you deep into radiation belts or even back out of Jupiter's gravitational influence. The burn must be perfect, which requires perfect calculations, perfect engine performance, and perfect fuel management. Assuming successful orbit insertion, you're now circling Jupiter. But you're not safe. Far from it. You're in an environment fundamentally hostile to human life, with radiation accumulating every minute, no possibility of resupply, and communications delay that prevents real-time assistance from Earth. If you develop a problem, you solve it yourself, or you die. Let's say your objective is to land on Ganymede, the largest moon and the one with its own magnetic field, providing some radiation protection. Ganymede orbits Jupiter at a distance of about 665,000 miles, taking 7 days to complete one orbit. From Jupiter orbit, you must wait for Ganymede to be in the right position, then perform another engine burn to match orbits with the Moon. This burn also requires fuel, more velocity change, more risk. Once you're in Ganymede orbit, you can begin descent to the surface. Ganymede's gravity is about 14% of Earth's gravity. It's enough that you need rockets to land, not just to avoid crashing, but to land softly enough that equipment isn't damaged. The surface is a mix of ice and rock, with ancient dark terrain heavily cratered and younger bright terrain showing grooves and ridges from past geological activity. There's no atmosphere, so no aerodynamic braking during descent. You must use rockets for the entire descent, burning fuel the whole way down. The landing must be gentle, because if you damage the spacecraft, there are no spare parts, no repair facilities. What you brought with you is all you have. Assuming successful landing, you're now on Ganymede's surface. The view would be extraordinary. Jupiter dominates the sky. A massive banded sphere 13 times wider than the full moon appears from Earth. You'd see the great red spot transiting across Jupiter's disk. You'd see other moons, tiny points of light crossing in front of Jupiter or casting shadows on the planet's clouds. The Sun is a bright star, much dimmer than we see from Earth because you're 5 times farther away. Sunlight provides only 4% of the illumination we receive on Earth. Solar panels work much less efficiently at Jupiter's distance. You need large arrays to generate adequate power, or you need nuclear power sources like radioisotope thermoelectric generators or a small nuclear reactor. The surface temperature is about -260 degrees Fahrenheit. Everything is frozen. Water ice is harder than rock at these temperatures. Your habitat would need active heating to maintain livable temperatures inside, and that heating requires power, lots of power, continuously. You deploy inflatable or rigid habitats, cover them with regolith for radiation shielding, set up life support systems, power generation, communications equipment. Every step requires EVAs, and every EVA exposes you to radiation. Ganymede's magnetic field provides some protection, but you're still receiving radiation doses far higher than anywhere on Earth or the Moon. Extended EVAs would be dangerous or impossible, depending on how exposed you are to Jupiter's radiation belts. Daily life on Ganymede would be a constant struggle against the environment. Every breath of air is recycled. Every drop of water has been through your body multiple times. Food comes from stored supplies or hydroponics if you can grow crops in artificial light with the limited power available. You can't go outside without a pressure suit. The surface is vacuum. There's no air, no pressure, no protection from radiation. Temperatures are so cold that exposed skin would freeze instantly. Metal becomes brittle. Plastics crack. Seals fail. Equipment designed for Earth conditions doesn't work properly at -260 degrees. You need specially designed gear, tested and rated for extreme cold and vacuum. And even with the best equipment, wear and tear accumulates. Suits develop leaks. Gloves lose flexibility. Boots crack. You can repair some things, but eventually parts wear out beyond repair and you have no replacements. Your mobility decreases over time as suits degrade. Eventually, you might be confined to the habitat, unable to go outside, trapped in a few hundred cubic feet of living space. The psychological reality of living on Ganymede would be crushing. You're 484 million miles from Earth, the only human presence in a vast, empty system. Jupiter fills the sky, a constant reminder of where you are, beautiful but alien. The other moons cross the sky on predictable schedules. You can predict when Io will transit Jupiter's face. You know when Europa will emerge from Jupiter's shadow. The solar system's clockwork is visible and measurable, but none of it involves Earth. Earth is a faint blue dot near the Sun, visible only with telescopes. Most of the time, Earth is lost in the Sun's glare, and you can't see it at all. You can send messages to Earth, but the delay is 35 to 52 minutes each way. You send a message, "We have a problem with the water recycling system," and wait 45 minutes for Earth's response. By the time you receive advice, the problem might have resolved itself, or worsened catastrophically, or you might have already fixed it using your own knowledge and improvisation. Earth's help is always too late to be useful in emergencies. You're truly on your own. And then there's the knowledge that you're probably never leaving. The fuel required to launch from Ganymede, escape Jupiter's gravity, and return to Earth is more than you could possibly have brought with you. The numbers don't work. Even if you landed with tanks full of fuel, which you didn't because you used most of it getting to Jupiter and landing on Ganymede, escaping Jupiter requires velocity changes of tens of thousands of miles per hour. To put this in perspective, the Apollo lunar module launched from the Moon's surface with about 5,000 pounds of fuel and achieved about 6,000 feet per second of velocity change. That was enough to escape the Moon's weak gravity and reach lunar orbit where the command module was waiting. From Ganymede, you need to escape Ganymede's gravity, which is weaker than the Moon's, but still significant. Then, you need to escape Jupiter's gravity, which is vastly stronger than the Moon's. The total velocity change is probably 30,000 to 40,000 miles per hour, maybe more depending on the trajectory. That's 6 to 8 times the delta V the lunar module achieved. Fuel requirement scales exponentially with delta V. You'd need not 6 or 8 times as much fuel, but possibly 50 to 100 times as much fuel. We're talking about hundreds of thousands of pounds of propellant for a small capsule. The mass ratio becomes absurd. The fully fueled spacecraft would need to be 95% fuel by mass just to achieve the delta V for Jupiter escape. That means the actual crew capsule, life support, crew, and everything else would be only 5% of the total mass. It's geometrically impossible. You can't build a spacecraft with those proportions and have it function. The alternative is nuclear propulsion, or some advanced technology we haven't developed. Nuclear thermal rockets, where a nuclear reactor heats hydrogen to create thrust. could theoretically achieve much higher specific impulse than chemical rockets. This means you get more velocity change per unit of fuel. With nuclear thermal propulsion, you might be able to escape Jupiter with fuel mass only 10 to 20 times the mass of the payload instead of 50 to 100 times. That's still enormous, but it might be geometrically feasible. The problem is that nuclear thermal rockets don't exist in flight-ready form. They were tested in the 1960s and 70s, but never flown in space. Developing them would take decades and billions of dollars. And you'd need to bring the nuclear rocket with you from Earth, which adds mass to the initial launch, which requires more fuel, which adds more mass. The exponential growth of required launch mass makes the mission nearly impossible, even with advanced propulsion. Let's imagine for a moment that somehow, against all odds, you manage to launch from Ganymede with enough fuel to escape Jupiter. The burn would be long and brutal, maybe an hour or more of continuous rocket firing. You'd feel acceleration press you into your seat, the first significant gravity you've felt in years. As you climb away from Ganymede, Jupiter's disk would slowly shrink. The radiation environment would change as you cross different regions of the magnetosphere. Eventually, you'd reach Jupiter's sphere of influence boundary, where the Sun's gravity becomes more significant than Jupiter's. You'd be in interplanetary space again, aimed toward Earth's orbit. But Earth isn't where it was when you left. Earth has orbited the Sun multiple times during your mission. You need to aim for where Earth will be when you arrive, not where it is now. The trajectory calculations are complex, possibly requiring gravity assists from other planets to match velocities with Earth. The return journey might take longer than the outbound journey because you're not following an efficient Hohmann transfer. You might spend 3 or 4 years traveling back, with dwindling supplies, aging equipment, radiation, damaged electronics, and a crew that's been in space for 6 or 7 years total by the time you reach Earth. The physical state of that crew would be catastrophic. 6 or 7 years in reduced gravity, even with exercise regimens, would cause bone loss, probably approaching 50%. Your skeleton would be as fragile as an 80 or 90-year-old's. Muscle mass would be severely depleted. Your heart would be weakened from years of not pumping against gravity. Radiation exposure would be catastrophic. Thousands of REM accumulated over years. Cancer would be almost certain. DNA damage throughout your body would cause premature aging and organ failure. Your immune system would be barely functional. When you finally approached Earth, the question would be whether your body could even survive re-entry. The deceleration forces during atmospheric braking and landing, several times Earth's gravity for minutes at a time, might be enough to fracture your weakened bones. Your heart might fail, trying to pump blood against G-forces it hasn't felt in years. You might die during landing, even though you successfully completed the mission. And all of this assumes everything goes right. No catastrophic equipment failures, no medical emergencies that can't be treated, no psychological breakdowns, no accidents during EVAs, no unexpected radiation events, no computer failures, no fuel leaks, no collision with space debris. Any one of these could be fatal, and over 7 years in deep space, the probability of something going wrong approaches certainty. Murphy's Law applies with a vengeance in space. If something can fail, it will fail eventually. The longer the mission, the higher the probability of mission-ending failure. This is why I can say with confidence that anyone who goes to Jupiter will never come back. Not because they wouldn't want to, but because the physics and biology make return functionally impossible. The radiation would likely kill them before they even tried to leave. If they survived long enough to attempt escape, the fuel requirements would probably be insurmountable. If they somehow launched with impossible amounts of fuel, the biological degradation from years in space would probably kill them during the return journey or landing. At every step, the odds are overwhelmingly against survival, let alone successful return. Compare this to Mars, which we discussed earlier. Mars is hard. Mars missions are probably one-way trips for economic and practical reasons. But Mars is at least theoretically survivable. You can land on solid ground. The radiation is high, but not immediately lethal. The gravity is low, but not negligible. You can potentially manufacture fuel from local resources. A permanent Mars settlement is difficult but conceivable. Jupiter is in a different category entirely. There's no scenario where humans live on Jupiter's moons long term. The radiation exposure would cause cancer and death within years. There's no way to manufacture fuel, because there's no industrial base and the radiation prevents extended surface operations. The distance makes resupply impractical. The gravity makes escape nearly impossible. Every aspect of Jupiter missions is not just difficult, but fundamentally incompatible with human survival. Let me also address the idea of mining Jupiter's atmosphere for resources. This comes up sometimes in discussions of future space development. Jupiter's atmosphere is about 90% hydrogen and 10% helium. Within that helium are traces of helium-3, a rare isotope that could theoretically fuel fusion reactors. Helium-3 is extremely rare on Earth because it's a light element that's escaped our atmosphere over geological time. The Moon has helium-3 implanted in its regolith by the solar wind. Jupiter's atmosphere has much more. If we ever develop practical fusion power plants using helium-3 as fuel, Jupiter could be a resource. The problem is extracting it. You'd need to descend into Jupiter's atmosphere, scoop up gas, separate the helium-3 from the much more abundant helium-4 and hydrogen, and then escape back to space. Descending into Jupiter's atmosphere is a one-way trip for current technology. The Galileo probe that descended into Jupiter's atmosphere in 1995 lasted about an hour before being crushed and vaporized by pressure and heat. It sent back data during its descent, measuring temperature, pressure, wind speeds, and composition. But it was destroyed long before reaching anything we'd call Jupiter's interior. An atmospheric mining vehicle would need to withstand pressures and temperatures far exceeding what any probe has survived. It would need to operate in an environment of supercritical hydrogen, where the distinction between gas and liquid breaks down. And then it would need to escape, accelerating upward through hundreds of miles of increasingly dense atmosphere against Jupiter's intense gravity. The energy required would be enormous. You'd probably expend more energy escaping than you'd gain from the helium-3 you collected. It's thermodynamically nonsensical. The economics don't work, even assuming perfect fusion technology. What about building floating platforms in Jupiter's upper atmosphere, where pressure and temperature are more moderate? At certain altitudes in Jupiter's atmosphere, about 100 to 200 miles above the visible cloud tops, pressure is similar to Earth's sea level pressure, and temperatures are around room temperature. In principle, you could imagine a platform or balloon station floating at this altitude. The problem is radiation. Even at these altitudes, you're still within Jupiter's magnetosphere, still being bombarded by charged particles. And there's no solid anchor. A floating platform would drift with Jupiter's winds, which blow at hundreds of miles per hour. You'd be in constant turbulence, buffeted by storms, with no way to maintain position. Lightning on Jupiter is far more powerful than Earth. Lightning, a single strike, could destroy a platform. And what's the purpose of this platform? You can't extract resources from the atmosphere without descending to much higher pressure regions. You can't access the moons because you're deep in Jupiter's gravity well. You can't use it as a base for exploration because Jupiter has nothing to explore except more atmosphere. A floating platform serves no practical purpose and faces insurmountable engineering challenges. The conclusion is inescapable. Jupiter is not a destination for human exploration. It will never be colonized. There will never be cities on Ganymede, or research stations on Europa, or mining operations in the atmosphere. These are science fiction dreams that don't survive contact with physical reality. Jupiter is too far, too dangerous, too fundamentally alien for human presence. We can admire it from Earth through telescopes. We can send robots to study it up close. But humans will never set foot on any part of the Jovian system and return alive. The first person to attempt it would be the last, dying in radiation and isolation on a frozen moon or crushed in the atmosphere. Billions of miles from home, with no possibility of rescue or return. This conclusion might seem pessimistic, but I don't see it that way. Understanding our limits is part of understanding our place in the universe. Not every world is meant for us. Some places exist to be studied, to expand our knowledge, to challenge our understanding of planetary science and atmospheric dynamics and magnetic fields. Jupiter serves that purpose beautifully. Every mission we send to Jupiter, every probe, every orbiter, every flyby, teaches us something new about how planets form, how magnetic fields work, how atmospheres behave. The Galilean moons are laboratories for studying tidal heating, subsurface oceans, volcanism, impact cratering, ice dynamics. We learn from Jupiter without being there, and that's enough. It has to be enough, because being there isn't possible. Let me explore more deeply why the radiation problem specifically makes human presence at Jupiter impossible. Because this single factor alone is sufficient to rule out human missions, even if we solved every other challenge. Radiation in space comes from several sources. Galactic cosmic rays are high-energy particles, mostly protons, that originate outside our solar system. They travel at nearly the speed of light and have so much energy that they pass through almost anything. Even thick shielding only reduces their impact. It doesn't stop them. Solar particle events are bursts of radiation from the sun, usually associated with solar flares or coronal mass ejections. These are lower energy than galactic cosmic rays, but come in much higher quantities during events. And then, there's trapped radiation in planetary magnetic fields. Earth has Van Allen belts, donut-shaped regions where charged particles are trapped by our magnetic field. Astronauts traveling to the moon had to pass through these belts quickly to minimize exposure. The belts are dangerous, but crossable in hours. Jupiter's radiation belts are incomparably worse. Jupiter's magnetic field is 20,000 times stronger than Earth's. This creates radiation belts that extend millions of miles from the planet and contain particles with millions of times more energy than Earth's Van Allen belts. The inner belts, which include the orbits of Io and Europa, receive radiation doses measured in thousands of rem per day. For context, 500 rem is lethal to humans. That's a cumulative dose over weeks or months that has 50% fatality rate. On Europa, you'd receive 500 rem in less than 3 hours. You'd be gone, in a day or two, from acute, radiation sickness. Your immune system would collapse. You'd experience nausea, vomiting, hemorrhaging, and organ failure. No treatment could save you. Even on the outer moons, like Ganymede and Callisto, where radiation is lower, you're still receiving doses hundreds of times higher than background on Earth. Ganymede's own magnetic field provides some protection, creating a mini magnetosphere that deflects some of Jupiter's radiation. But Ganymede orbits within Jupiter's larger magnetosphere, so you're still exposed to significant radiation. Current estimates suggest radiation on Ganymede's surface is about 50 to 100 rem per day. That's still dangerous. Spend 10 days on Ganymede's surface, and you've received a potentially lethal dose. Spend a month, and you're gone. Long-term habitation would require living underground, buried under meters of ice or rock to block radiation. But even underground, cosmic rays still penetrate. Some shielding helps, but you can't eliminate exposure completely. Over months and years, the cumulative dose builds. Cancer becomes inevitable. Your DNA accumulates damage faster than cellular repair mechanisms can fix it. Mutations occur. Cells become cancerous. Multiple cancers develop simultaneously because every cell in your body has been damaged. There's also a more insidious effect of radiation that's often overlooked. High-energy particles don't just damage cells, they also create secondary radiation. When a high-energy particle hits the nucleus of an atom in your body or in spacecraft shielding, it can shatter that nucleus into fragments. These fragments are also radioactive and also damage nearby cells. This is called a cascade shower, and it means that thick shielding can sometimes make radiation exposure worse, not better. A particle hits the outer layer of shielding, creates fragments. Those fragments hit more atoms, creating more fragments. And by the time the cascade reaches the inside of the spacecraft, you have more total particles than you started with, just at lower individual energies. The only shielding that works well against high-energy cosmic rays is hydrogen-rich material like water or polyethylene. Hydrogen nuclei are light, so they don't fragment when hit by high-energy particles. They just absorb energy and maybe create a few low-energy neutrons. But you need meters of water to achieve significant radiation reduction. A spacecraft surrounded by meters of water shielding would be impossibly heavy. The mass would be enormous, requiring massive fuel to accelerate and decelerate. It's not practical. So radiation at Jupiter is fundamentally unsurvivable for humans without shielding we can't build. No amount of clever engineering changes this. You'd need to surround habitats with dozens of feet of water or regolith, creating structures so massive they couldn't be launched from Earth or constructed on site without industrial infrastructure that doesn't exist. You're trapped in an impossible situation. You need heavy shielding to survive, but heavy shielding can't be transported or constructed, so you can't survive. Now, let's discuss the communications challenges in more detail, because the isolation of a Jupiter mission is more severe than people realize. Light, and therefore radio signals, travels at about 186,000 miles per second. Jupiter, at its closest, is about 390 million miles from Earth. Radio signals take about 35 minutes to travel from Jupiter to Earth. That means communication has a round-trip delay of 70 minutes. You send a message, wait 35 minutes for it to reach Earth, then wait another 35 minutes for Earth's response. More than an hour for a single exchange. When Jupiter and Earth are on opposite sides of the Sun, the distance increases to about 600 million miles, and the delay increases to about 52 minutes each way, over 100 minutes round trip. For normal communications, this is annoying but manageable. You send messages, wait for replies, conduct your mission, knowing that conversations are more like letter writing than real-time discussion. But for emergencies, the delay is potentially fatal. If life support fails, if there's a fire, if someone is injured, you can't get immediate advice from Earth. You send a distress message. Our oxygen scrubber is failing, carbon dioxide is building up, and then you wait over an hour for a response. In that hour, carbon dioxide might reach lethal levels. You have to solve the problem yourself, using whatever knowledge and resources you have on site. Earth's eventual response might contain useful troubleshooting steps, but by the time it arrives, you've either fixed the problem or you're gone. This is fundamentally different from ISS operations, where mission control monitors systems in real time and can alert crews to problems before they notice them. On the ISS, if a computer detects an anomaly, mission control sees it within seconds and can immediately radio the crew. Decisions are made collaboratively between crew and ground support. At Jupiter, the crew is completely autonomous. They monitor their own systems, diagnose their own problems, make their own decisions. Earth becomes a distant consultant who provides advice hours late, useful for long-term planning, but irrelevant for immediate crises. The psychological impact of this isolation compounds over time. Initially, it might feel like an adventure. You're farther from Earth than anyone has ever been, exploring the Jovian system, conducting groundbreaking research. But as months turn into years, the isolation becomes oppressive. You can't call home and have a real conversation with family. You send messages and receive responses hours later, but it's not the same as talking. The emotional support that communication normally provides is absent. You're functionally alone, even though you can technically exchange messages. Relationships with family and friends on Earth become strained or break entirely. People move on with their lives. They can't relate to your experience. You can't relate to theirs. You're living in completely different worlds. Earth events, politics, news, culture, all of it becomes distant and irrelevant. What does it matter who won an election when you're 484 million miles away, dealing with failing equipment and radiation exposure? You become disconnected from humanity in a profound way. The crew would develop their own culture, their own internal references, their own ways of coping. But with only 4 to 6 people, the social dynamics are fragile. If conflicts develop, there's no escape. You can't avoid someone or take time apart when you're living in a few hundred cubic feet of space. Every personality quirk, every annoying habit, every disagreement gets magnified over years of proximity. Research on small, isolated groups shows that mission failure often comes from social breakdown rather than technical problems. The crew stops functioning as a team. Communication breaks down. People stop cooperating. In extreme cases, violence occurs. On a Jupiter mission, social breakdown would be fatal. The mission requires cooperation. Systems need maintenance. Problems need solving. If the crew isn't working together, systems fail and people die. There's no mission control to mediate conflicts or provide external perspective. The crew has to resolve problems internally or live with them, and living with unresolved conflict for years in close quarters is psychologically devastating. Let me also address the question of what we'd actually do at Jupiter if we somehow got there and survived. What scientific research justifies the enormous cost and risk? The most compelling target is Europa's subsurface ocean. If life exists in that ocean, it would be one of the most important discoveries in human history. It would prove that life can arise independently in multiple locations, that we're not alone in the universe, that the conditions for life are more common than we thought. Finding life on Europa would revolutionize biology, astrobiology, and our understanding of our place in the cosmos. But do we need humans to make that discovery? Robotic missions can drill through Europa's ice, lower cameras and sensors into the ocean, collect samples, and send data back to Earth. Robots don't need life support. They can tolerate radiation that would kill humans instantly. They don't experience psychological stress. They can operate for years and then fail. Mission complete, without the moral weight of human death. The Europa Clipper mission, scheduled to arrive at Jupiter in 2030, will conduct dozens of close flybys of Europa, using ice-penetrating radar to map the ocean beneath the ice, measuring the thickness of the ice shell, analyzing the chemistry of the surface. If it detects promising locations, future missions could land and drill. All of this can be done robotically, more safely, more cheaply, and more effectively than sending humans. What about studying Jupiter itself? The atmosphere, the magnetic field, the interior structure? Again, robots are better suited. Atmospheric probes can descend into the clouds, measuring conditions far beyond what any human-rated spacecraft could survive. The Galileo probe sent back data from 60 atmospheres of pressure and temperatures over 300 degrees Fahrenheit before being destroyed. A human spacecraft could never descend that far. Orbiters like Juno can map Jupiter's magnetic field, measure gravitational anomalies that reveal interior structure, and study the auroras at the poles, all from safe distances and without life support requirements. The scientific case for sending humans to Jupiter is weak. Robots can do the science better and cheaper. The only argument for human presence is flexibility and adaptability. Humans can respond to unexpected situations, make judgment calls, repair equipment in creative ways. On Mars, this might justify human missions despite the challenges. Mars is accessible enough that the advantages of human presence might outweigh the costs. At Jupiter, the costs are so extreme that any advantages of human presence are swamped. You'd spend so much effort just keeping humans alive that actual science would be minimal. The crew would be occupied with maintenance, repairs, survival. Time for research would be limited. And the radiation exposure would be so severe that crew members would be dying of cancer before the mission could accomplish significant science goals. It's not worth it. Let me paint one more scenario to illustrate why Jupiter missions are impossible. Imagine we developed nuclear thermal propulsion, dramatically reducing fuel requirements. Imagine we developed advanced radiation shielding, reducing exposure to marginally survivable levels. Imagine we had perfect closed-loop life support that could operate for decades. Imagine we solved every technical challenge I've described. Even with all these advances, a Jupiter mission still faces one insurmountable problem: biology. Human bodies are not designed for years in deep space, followed by years on a low-gravity moon in a high-radiation environment. The physical degradation is cumulative and irreversible beyond a certain point. Bones lose density. Muscles atrophy. The cardiovascular system deconditions. The immune system weakens. Radiation damages DNA. Cells become cancerous. And there's a threshold beyond which the body can't recover. We don't know exactly where that threshold is because no human has spent 5 to 7 years in deep space. But studies on ISS astronauts suggest that 2 to 3 years might be close to the limit. Beyond that, the body might be too damaged to ever function normally again, even with extensive rehabilitation. A Jupiter mission requires 5 to 7 years minimum, 2 years outbound, 1 to 3 years at Jupiter for science, and waiting for launch windows, 2 years return. That's longer than anyone has spent in space consecutively. The crew would arrive back at Earth, if they arrived at all, with bodies so damaged they might not survive landing. Their bones might fracture during re-entry deceleration. Their hearts might fail, trying to pump blood against Earth gravity. They might develop multiple cancers simultaneously from radiation exposure. Even if they survived landing, they'd need years of rehabilitation and would probably never fully recover. They'd live shortened lives, with chronic health problems as a direct result of the mission. Is it ethical to send people on a mission knowing it will permanently destroy their health, even if they survive? That's a question without easy answers, but it's worth asking. Compare this to Antarctica expeditions in the early 20th century. Ernest Shackleton's crew survived years in Antarctic conditions and returned, mostly healthy. Modern Antarctic researchers spend months or even years at research stations and return to normal life. The environment is harsh, but it's survivable with proper equipment and shelter. Jupiter is not survivable, not with any equipment we can imagine building. The environment is so hostile that mere presence is a slow death sentence. Every day at Jupiter is damage accumulation. There's no threshold where you adapt and survive. You only survive as long as your body can tolerate the accumulated damage, and then you die. This brings me to the philosophical question of whether we should go, even if we could. Is there value in human presence at places fundamentally incompatible with human life? Some would argue, yes, that pushing boundaries and exploring the unknown is intrinsically valuable, regardless of practical outcomes. The explorer spirit, the desire to see what's over the next hill, is part of what makes us human. We climb mountains because they're there, not because there's practical value at the summit. Going to Jupiter would be the ultimate mountain, the ultimate challenge. But mountains on Earth don't kill you just by being there. They're dangerous because of objective hazards like falls, avalanches, and exposure. With skill and preparation, mountains can be climbed safely. Many people reach the summit and return. Jupiter isn't like that. Jupiter kills you through radiation, through isolation, through physiological degradation, through challenges that skill and preparation can't overcome. It's not a mountain to climb, it's a meat grinder that destroys everyone who enters. There's no skill level that makes Jupiter survivable. There's no amount of preparation that changes the outcome. Perhaps the value is symbolic. Sending humans to Jupiter would demonstrate our capability, our commitment to exploration, our willingness to take risks for knowledge. But symbolic gestures that kill everyone involved aren't heroic, they're wasteful. We can honor the explorer spirit by pushing boundaries where success is possible. Mars is incredibly difficult, but it's possible. Establishing a permanent presence on Mars would be a worthy achievement that demonstrates human capability without being a suicide mission. Jupiter is beyond possible. It's in the realm of fantasy, and pretending otherwise does a disservice to real exploration. Let me close by considering what the far future might hold. Could advanced civilizations, thousands of years from now, visit Jupiter? Maybe. If we develop technologies that seem like magic to us now, like artificial gravity, perfect radiation shielding, fusion drives that make Jupiter as accessible as the Moon is to us. Perhaps future humans, or their descendants, could explore Jupiter safely. But those civilizations would be so far beyond our current capabilities that we can barely imagine them. They wouldn't be us. They'd be something else, something adapted to space through technology or evolution or both. And even then, Jupiter might remain too hostile. Some challenges don't have technological solutions. Some places are fundamentally incompatible with biological life. Jupiter might be one of those places for any biology we can imagine. In practical terms, within the next century, or even the next few centuries, no human will visit Jupiter. The challenges are too extreme. The technology required doesn't exist and might not be developable. The biological limits are fundamental and unchangeable. Jupiter will remain a realm explored by robots, observed through telescopes, studied remotely. And that's fine. That's appropriate. We don't need to go everywhere. We don't need to plant flags on every world. Some places are meant to be appreciated from a distance, studied but not touched, admired but not possessed. Jupiter has taught us about planetary formation, about magnetic fields, about atmospheric dynamics. Its moons have taught us about tidal heating, subsurface oceans, and volcanism. Future robotic missions will teach us even more. Perhaps we'll find life in Europa's ocean. Perhaps we'll discover new moons. Perhaps we'll unravel the mysteries of Jupiter's interior structure and understand how gas giants form and evolve. All of this knowledge will come from robotic exploration, from instruments and cameras sent to brave the radiation and return data before being destroyed. And that's valuable. That's worthwhile. We'll learn about Jupiter without dying at Jupiter, which is the best possible outcome. So when someone asks whether humans will ever go to Jupiter, the honest answer is no. Not in our lifetimes. Not in our children's lifetimes. Probably not ever. Jupiter is too far, too hostile, too fundamentally alien. It's a planet for robots, not for people. And anyone who tried to go, despite all the warnings, despite all the physics and biology and engineering saying it's impossible, would never come back. They wouldn't fail to return because they chose to stay. They wouldn't fail to return because of politics or economics. They'd fail to return because they'd be gone, killed by radiation or isolation or equipment failure, or the simple impossibility of escaping Jupiter's gravity with any fuel mass that could realistically be carried. Their death would be neither quick nor heroic. It would be slow, painful, isolated, and ultimately pointless. That's the truth about Jupiter missions. Not inspiring, not optimistic, but honest. And sometimes honesty is more valuable than inspiration. Sometimes acknowledging limits is wiser than ignoring them. Jupiter is one of our solar system's greatest wonders, a massive world that challenges our understanding and expands our knowledge. We should celebrate it for what it is and study it with the tools we have. But we should also accept that it's not a place for humans and never will be. Some boundaries are meant to be respected, not crossed. Let me delve even deeper into the specific technical challenges that make Jupiter impossible, because understanding the engineering details makes the impossibility clearer. Consider the spacecraft design required for a Jupiter mission. You need a vessel that can support 4 to 6 humans for 5 to 7 years in deep space. The ISS, which supports 3 to 7 crew members, has a pressurized volume of about 32,000 cubic feet spread across multiple modules. It weighs about £920,000. For a Jupiter mission, you'd need similar volume, but with completely independent systems, since resupply is impossible. You'd need redundancy in every critical system: life support, power generation, computers, communications, thermal control. The spacecraft mass would probably exceed £1 million. Now, add radiation shielding. Water is effective radiation shielding, providing protection roughly equivalent to the same mass of other materials, but with the advantage of being useful for other purposes like drinking, cooling, and propellant production. To reduce radiation exposure by a factor of 10, you'd need about 6 feet of water surrounding the crew compartment. The volume of water needed depends on the geometry, but for a cylindrical crew module, 10 feet in diameter and 20 feet long, surrounded by 6 feet of water on all sides, you'd need about 40,000 cubic feet of water. Water weighs 62 pounds per cubic foot, so that's about 2.5 million pounds of water just for shielding. Your total spacecraft mass is now over 3.5 million pounds before you add any fuel. Chemical rocket fuel has specific impulse of about 370 seconds for methane and oxygen. To calculate fuel requirements, we use the Tsiolkovsky rocket equation. Delta V equals exhaust velocity times natural log of initial mass divided by final mass. Exhaust velocity for methane-oxygen is about 11,800 feet per second. To enter Jupiter orbit requires delta V of about 40,000 feet per second. Plug in the numbers and you get a mass ratio of about 40:1. For every pound of spacecraft, you need 40 pounds of fuel. For a 3.5 million pound spacecraft, you need 140 million pounds of fuel just to enter Jupiter orbit. That's absurd. No rocket we've ever built could lift that much mass from Earth. The Saturn V, the largest rocket ever flown successfully, could lift about 260,000 pounds to low Earth orbit. You'd need over 500 Saturn V launches to deliver enough fuel to Jupiter orbit, and that's before accounting for the mass of the fuel tanks themselves. You might argue that we should use nuclear propulsion with higher specific impulse. Nuclear thermal rockets could theoretically achieve specific impulse of 900 seconds, more than double chemical rockets. This reduces the mass ratio requirement. With nuclear propulsion, entering Jupiter orbit might require a mass ratio of only 6:1 instead of 40:1. That means 21 million pounds of propellant for a 3.5 million pound spacecraft. Still enormous, but geometrically possible. The problem is that nuclear rockets don't exist in flight-ready form. The NERVA program, in the 1960s and 70s, built and tested nuclear thermal rocket engines on the ground. They worked, achieving specific impulses around 800 seconds, but they were never flight-tested. Developing flight-qualified nuclear rockets would require billions of dollars and decades of work. You'd need to solve problems like reactor cooling during long coast phases, radiation shielding for the crew from the reactor, safe startup and shutdown procedures, and what to do with radioactive components after the mission. None of these are insurmountable, but all require extensive development. Even with nuclear propulsion, you still face the problem of launching from Earth. A 3.5 million pound spacecraft with 21 million pounds of propellant is 24.5 million pounds total. That's more than 90 times the payload capacity of a Saturn V. You'd need to assemble the spacecraft in Earth orbit using dozens of launches, or develop a new super heavy lift vehicle far larger than anything that exists. SpaceX's Starship, if it becomes operational, might be able to lift 220,000 to 300,000 pounds to low Earth orbit. You'd still need 80 to 100 launches to deliver all the components and propellant. The cost would be staggering, probably hundreds of billions of dollars just for the launches, before accounting for spacecraft development, mission operations, and everything else. And remember, this enormous effort just gets you to Jupiter orbit. It doesn't land you on any moons. Landing on Ganymede requires additional propellant for descent and ascent. Ganymede's escape velocity is about 6,400 feet per second. With chemical rockets, landing and taking off again requires a mass ratio of about 2 to 1. Half the mass that arrives at Ganymede must be propellant for landing and launch. With nuclear propulsion, the ratio is better, but still significant. And then you need fuel to escape Jupiter's gravity well and return to Earth. Jupiter's escape velocity from Ganymede's orbit is about 49,000 feet per second. Add Ganymede's own escape velocity, and you need about 55,000 feet per second total delta V to go from Ganymede's surface to Jupiter escape. With nuclear propulsion at 900 seconds specific impulse, that's a mass ratio of about 7 to 1. For every pound of spacecraft that eventually heads back to Earth, you need 7 pounds of fuel at Ganymede's surface. If you want to return a crew capsule weighing 20,000 pounds, you need 140,000 pounds of propellant at Ganymede for the escape burn. But you also needed propellant for landing, probably another 40,000 pounds. So you need 180,000 pounds of propellant delivered to Ganymede's surface. Getting that propellant to Ganymede from Jupiter orbit requires more propellant because of the mass ratio problem. The numbers spiral out of control quickly. You might propose manufacturing propellant on Ganymede using local resources. Ganymede probably has water ice that could be melted and electrolyzed into hydrogen and oxygen for rocket fuel. But this requires energy, lots of energy. Electrolyzing 180,000 pounds of water into hydrogen and oxygen requires about 300 million kilowatt-hours of electricity. For comparison, a typical nuclear power plant generates about 1 million kilowatts. Running continuously, it would take that plant 300 hours, or about 12.5 days, to generate enough electricity. But you don't have a nuclear power plant on Ganymede. You have solar panels that work at 4% efficiency compared to Earth, because Jupiter is 5 times farther from the Sun. Generating 300 million kilowatt-hours with solar panels would take years, assuming you had massive solar arrays and perfect energy storage. And you'd need mining equipment to extract ice, heating systems to melt it, electrolysis systems to split it, compressors to liquefy the hydrogen and oxygen, storage tanks to hold the propellants, and all of this operating in minus 260-degree temperatures while being bombarded by radiation. The industrial infrastructure required is enormous, far beyond what could be transported from Earth or built by a small crew. Let's consider what happens if, despite all these impossibilities, you somehow reached Ganymede with a small crew. Your daily activities would be dominated by survival, not exploration. Each morning, or what passes for morning in the eternal twilight of Ganymede, you'd check life support systems. Carbon dioxide scrubbers need monitoring. If they fail, carbon dioxide accumulates and you suffocate. Water recycling systems need maintenance. Filters clog and must be cleaned or replaced. Oxygen generation requires power and must be monitored constantly. Any drop in oxygen levels is an emergency. Temperature control systems must be checked. Ganymede's surface is minus 260 degrees. If heating fails, the habitat temperature plunges and you freeze. Power systems, whether solar or nuclear, need monitoring. If power fails, everything else fails within hours. You'd spend hours each day on these checks and on routine maintenance. Then there's food production. Stored food has limited shelf life. For a multi-year mission, you'd need to grow some of your own food using hydroponics or aeroponics. Growing plants in artificial light requires significant power and careful attention. Plants need nutrients, water, correct temperature, correct light spectrum, and intensity. Diseases can wipe out crops. Equipment failures can kill entire harvests. You'd need to maintain seed stocks, care for plants daily, harvest and process food, manage crop rotation for variety and nutrition. This takes time, several hours per day for a small crew. Medical monitoring would be essential. Radiation exposure needs tracking. Each crew member would have dosimeters measuring accumulated dose. If someone approaches dangerous levels, they'd need to spend more time in shielded areas or reduce EVA frequency. Psychological health needs attention too. Crew members need to talk about stress, conflicts, homesickness. Ignoring mental health in isolated groups leads to breakdowns. Exercise is mandatory to slow bone and muscle loss. Each crew member would need several hours daily of resistance training and cardiovascular work. Without it, physical degradation accelerates. After all these survival activities, there's limited time for actual science. Maybe a few hours per day could be devoted to exploration, experiments, data collection. That's vastly less than what robots could accomplish, because robots don't need life support, exercise, food production, or psychological support. Now, let's imagine a specific failure scenario to understand how fragile these missions would be. You're 6 months into surface operations on Ganymede. The crew of 4 has established a routine. Systems are working, food is growing, science is being done. Then one day, a micrometeorite, smaller than a grain of sand, hits a water tank at tens of thousands of miles per hour. It punches a tiny hole through the tank wall. Water begins leaking into the vacuum, immediately freezing into ice. The leak is slow, only a few pounds of water per day, but it's constant. You detect it when water inventory doesn't match consumption records. You investigate, find the leak, realize you need to patch it. Patching requires an EVA. Someone suits up, goes outside into the radiation, examines the tank. The hole is microscopic, but real. You use sealant to patch it, but you've lost about 50 pounds of water total. That doesn't sound like much, but over years, small losses accumulate. Every leak, every system inefficiency, every unexpected loss reduces your margin for survival. You can't replace lost water easily. Mining ice requires energy and equipment. Your margins grow thinner. A few months later, a solar panel develops a crack, possibly from thermal cycling as it swings between extreme temperatures. Power output drops by 5%. You still have enough power for critical systems, but less margin for contingencies. You can't replace the panel. You have no spares that big. You'll just have to live with reduced power and manage consumption carefully. Another month passes, and someone develops a kidney stone, possibly from altered calcium metabolism due to low gravity and radiation exposure. The pain is severe. You have medical supplies, pain medication, but no surgery capability. Kidney stones usually pass on their own, but it's agonizing, and the crew member is incapacitated for days. If complications develop, if the stone doesn't pass, if infection sets in, there's nothing you can do. The person might die from something that would be a minor medical issue on Earth. These aren't dramatic catastrophes, they're mundane failures that accumulate. Every system has a failure rate. Over years, failures are inevitable. Some you can work around. Some degrade your capabilities. Some are fatal. The longer the mission, the higher the probability that a fatal failure occurs. On a 7-year mission, the cumulative probability of mission-ending failure approaches 100%. It's not a question of if something catastrophic goes wrong, but when. Compare this to Antarctic research stations again. McMurdo Station, the largest Antarctic research station, supports over 1,000 people in summer and about 200 in winter. It has extensive facilities, workshops, medical clinics, communications, power generation. Planes and ships bring supplies regularly. If someone gets seriously ill, they can be evacuated, weather permitting. If critical equipment fails, replacements can be flown in. The station is difficult to operate, but it's connected to global infrastructure. Help is possible, resupply is regular, evacuation is an option. A Ganymede base would have none of this. No resupply, no evacuation, no backup, no help. You'd be operating a complex facility with 4 to 6 people, no industrial support, no ability to manufacture most spare parts, no outside assistance. It's not sustainable. Equipment wears out faster than you can repair or replace it. Eventually, something critical fails, and you can't fix it, and you die. Let me also address the argument that we should start with smaller missions and build up capability gradually. Maybe send an unmanned cargo mission, first to pre-position supplies. Then send a small crew for a short surface stay, like Apollo did with the Moon. Then gradually extend mission duration and crew size. This is how we'd approach Mars, and it's sensible for Mars. But Jupiter is different. The distances and radiation make even the smallest crewed mission extraordinarily difficult. A short surface stay doesn't help because the travel time dominates. You still spend 4 years in transit for a 2-week surface visit. The cost and risk are only marginally better than a long-duration mission. And pre-positioning supplies requires solving the same fuel and propulsion problems as crew missions. You can't bootstrap your way to Jupiter capability the way you might for Mars. Jupiter requires solving the hardest problems first, and those problems might not have solutions. Some people argue that if we devoted the resources of the Apollo program to Jupiter missions, we could do it. Apollo was a massive national effort that spent about $150 billion in current dollars. It mobilized hundreds of thousands of people, developed new technologies, and achieved the goal of landing humans on the Moon. But the Moon is 3 days away, with communication delays of seconds. Radiation exposure is low because lunar missions only spend a week in space total. Lunar gravity is weak enough that chemical rockets can easily achieve escape velocity. The Moon is achievable with 1960s technology and enormous effort. Jupiter is not achievable with current technology and infinite effort because some challenges are fundamental, not engineering problems waiting for enough resources. You can't throw money at physics and change the laws of nature. Radiation at Jupiter will always be extreme. The distance will always be 484 million miles. At minimum, gravity will always require huge delta V to escape. These aren't problems that more funding solves. The only technology that might enable Jupiter missions is something we can barely imagine, like controlled manipulation of space-time to travel faster than light, or generation of artificial gravity fields to shield against radiation. These are science fiction technologies that might violate known physics. We can't develop them through engineering effort because we don't know if they're possible. Maybe in 1,000 years, if humanity survives and continues advancing, someone will figure out physics we don't understand and develop capabilities that seem magical to us. But we can't plan missions based on technologies that might be impossible. We have to work with what we have and what we can reasonably develop in the next few decades. And with those constraints, Jupiter is out of reach for humans. Let me consider one final thought experiment. Suppose an eccentric billionaire decided to fund a Jupiter mission privately, accepting that it would be a one-way trip. Volunteers were recruited who understood they'd never return. Enormous resources were devoted to developing the necessary technology. Could it be done? In principle, maybe. You could launch enough mass to Earth orbit over many years. You could assemble a spacecraft with adequate shielding and life support. You could use nuclear propulsion to reduce fuel requirements. You could send a crew on a one-way mission to orbit Jupiter or land on Ganymede, but the crew would die. Not might die, would die. Radiation exposure over years would give everyone cancer. Equipment failures would eventually become fatal because there's no resupply or rescue. Even if some crew members lasted a few years, none would last a decade. You'd be funding an elaborate suicide mission, sending people to certain death for marginal scientific gain. Is that ethical? Is it morally acceptable to send people on missions where death is certain rather than merely probable? These questions have no easy answers, but they're worth asking. Throughout history, explorers have died in pursuit of knowledge and discovery. Many Arctic and Antarctic expeditions ended in death. Many mountaineering expeditions have been fatal. But those explorers had a chance of survival. The risks were high, but not certain. Some explorers succeeded and returned. Their knowledge and experience informed future expeditions. A Jupiter mission offers no such possibility. Success would still end in death. There's no return, no knowledge gained that helps future crews survive, because the problems are fundamental. You're not learning how to survive Jupiter, you're just delaying the inevitable while radiation and equipment failures kill you slowly. That's the core reality of Jupiter missions. They're not exploration in any traditional sense. They're slow-motion suicide with scientific justification. The crew would spend years traveling to Jupiter, knowing they're accumulating radiation damage that will kill them eventually. They'd conduct research on Ganymede or Europa, knowing each EVA shortens their lives. They'd watch equipment fail and margins shrink, knowing rescue is impossible. And they'd die on an alien moon, probably from cancer or equipment failure, or both, having accomplished science that robots could have done better and more safely. There's no heroism in pointless death. There's no glory in sacrificing people for research that doesn't require human presence. We honor explorers who took calculated risks in pursuit of knowledge. We don't honor suicides. This is why I can say with confidence, anyone who goes to Jupiter will never come back. It's not pessimism, it's physics and biology and engineering reality. The challenges are too extreme, the dangers too severe, the timescales too long. Human bodies can't survive the radiation. Human psychology can't tolerate the isolation. Human technology can't overcome the fundamental problems of distance, gravity, and power requirements. Jupiter is a boundary we cannot cross. Not yet, probably not ever. And that's okay. Not every place needs to have human footprints. Not every world needs to be conquered. Some places are meant to remain beyond our reach, studied and admired, but never visited. Jupiter is one of those places, magnificent and deadly, fascinating and impossible, forever beyond the grasp of human exploration. Good night, and remember that the universe is vast and full of wonders, but not all wonders are meant for us. Some are meant to remain mysteries, viewed from a distance, appreciated but never possessed. Jupiter is one of those wonders, and perhaps that makes it more special, not less.